Hello everyone, my name is Sophie, and in this video will cover Module 13, the topic being turning vegetable oil into biodiesel. In this video, I'll be covering the structure of vegetable oil, followed by how to prepare oil for transesterification. Next, I'll look at what is catalytic transesterification and the two methods that are associated with catalytic transesterification. I'll be looking at the advantages and disadvantages of the two above methods. Then I'll be looking into a third method, non-catalytic transesterification. This will follow with the structure and properties of biodiesel, along with the benefits, and then real-world applications, such as laboratory steps for base catalyzed transesterification, and a do-it-yourself on repurposing your own used oils to eventually make biodiesel. So we'll start off with what is the structure of vegetable oil. Vegetable oil is composed of triglycerides. Triglycerides are esters formed by the reactions of three free fatty acids, which have a hydrocarbon chain in a functional group, plus glycerol. Glycerol provides the three-carbon backbone, and the fatty acids provide acyl groups. The molecular structure of vegetable oil is large and branched. Vegetable oil remains liquid at fairly low temperatures due to the predominance of unsaturated fatty acids and has a high viscosity. There are a few steps that must be done to prepare vegetable oil. Prior to transesterification, water must be removed so it does not hydrolyze, producing soap stock instead of biodiesel. Degumming may be used in some cases to remove phospholipids and other plant matter. And lastly, recycled oils are refined from impurities such as dirt or charred food. Now, what is transesterification? Transesterification is the conversion of a carboxylic acid ester into a different carboxylic acid ester. When an ester is placed in large excess of an alcohol along with an acid or base catalyst, there is an exchange of alkoxy groups. Since both the reactants and the products are an ester and an alcohol, the reaction is reversible and the equilibrium constant is close to 1. Moving on to base catalyzed transesterification. This is one process vegetable oils may undergo to produce biodiesel. 3 moles of alcohol, generally methanol or ethanol, are used since they are the cheapest and most abundant, react with 1 mole of triglycerides. A strong base such as sodium hydroxide or potassium hydroxide is used as a catalyst. The added alcohol is deprotonated with a base to make it a stronger nucleophile. The result is 3 moles of biodiesel and 1 mole of glycerol. Alcohol will remain in the products and must be removed and recovered. The reaction proceeds quickly, then slows when reaching equilibrium. Producers will often add 1.6 to 2 times the amount of methanol to ensure the reaction is driven to completion. The general mechanism in basic conditions is that the carbonyl group of the starting ester of vegetable oil undergoes a nucleophilic attack by the incoming alkoxide from the base catalyst to give a tetrahedral intermediate. This either reverts to the starting material or proceeds to the transesterified product. Then the leaving group is removed. The transesterification process is catalyzed by Bronsted acids, most commonly sulfuric acid. These acid catalysts give very high yields in alkyl esters. Increasing the amount of catalyst used makes the reaction occur quicker, or increases the reaction rate. This is used less frequently and commercially due to the slower rate compared to base catalyzed. The mechanism for acid-catalyzed transesterification is as follows. There's protonation of the carbonyl by the acid catalyst. This makes the carbonyl activated towards nucleophilic attack. A nucleophilic attack is made on the carbonyl. There is then a proton transfer, removal of the leaving group, and finally deprotonation. There are a few problems with catalytic transesterification. The process is relatively time-consuming and requires the separation of the vegetable oil, alcohol, catalyst, and impurities mixture from the biodiesel. The wastewater generated through biodiesel purification is also not environmentally friendly. Acid-catalyzed transesterification reactions are slow, requiring temperatures above 100 degrees Celsius and more than 3 hours to reach complete conversion, thus raising the cost. Next, I'm going to look at the non-catalytic transesterification method. This technique is called supercritical alcohol transesterification. During transesterification, long chains of triglycerides transform to monoesters and glycerol. As temperature increases, polarity of alcohol declines. Nonpolar triglycerides can be well solvated with supercritical alcohol to form a single phase. The reaction occurs spontaneously and rapidly. The purification of biodiesel is also much easier since no catalyst is required. This also eliminates and prevents soap formation or saponification. The issues of supercritical alcohol transesterification are the high temperature and pressure required for reaction to proceed, and the expensive price tag for the apparatus. Next, we'll look at the structure of biodiesel. Biodiesel is a monoalkyl ester of long straight-chain fatty acids. Converting vegetable oil to biodiesel makes it a smaller molecule and less likely to get to gel in cold temperatures. Biodiesel, because it contains oxygen, is more polar than standard diesel and therefore more prone to freezing or gelling. Esters of biodiesel and diesel are very similar. Next, we're looking at the benefits of biodiesel. Biodiesel is a renewable energy source. Recycling the oil eliminates risk of sewage clogging. Biodiesel engines can burn fuel the same as diesel to run automobiles. And lastly, reusing waste oil limits negative effects on the environment by limiting fossil fuels to produce standard diesel. If you were to do a base catalyzed transesterification in a lab, these would be the steps you would follow. First, you would measure out 1 gram of potassium hydroxide into a 250 milliliter Erlenmeyer flask. Next, you would add 6 times the ratio of ethanol to triglycerides used. You would put this on a hot plate and stir, and cover with aluminum foil. You'd be mixing until the potassium hydroxide is fully dissolved. You're going to leave separately, and then measure vegetable oil into a separate 250 milliliter Erlenmeyer flask, adding in a stir bar and heat to 60 degrees Celsius. You're going to add in your alcohol catalyst mixture to the oil, and you're going to cover with aluminum foil or watch glass. Now you're going to stir moderately for 60 minutes at 60 degrees Celsius. You're going to then transfer the mixture to a funnel so that you can cool and separate for 20 minutes. You're going to remove the lower level of glycerol into the glass. This upper layer that's left is biodiesel, and the separated lower level is crude glycerol with remaining catalyst. Now, after using cooking oil, instead of throwing it out, you can prepare it for recycling. Using any excess oil from vegetable oil to tuna oil, after cooking, you're going to let the oil cool down. Next, transfer it to a clean container using a funnel or a sieve. There are many locations of recycling services that individuals can drop off your now purified oil. Lastly, the oil will be collected and taken to a processing plant to turn into biodiesel. Thank you so much for listening to my tutorial, and I hope you learned a little bit about the process of transesterification and the next steps that you can do.